Hi, my name is Mark Knutson. I'm an application engineer with Keysight Technologies, working with PathWave System Design tools. And we recently came out with a new update to our SystemVue tool called 2020 Update 1. And I'd like to give you a deeper dive look into one of the new features, which involves, if you're a receiver designer, this is going to be of supreme interest to you. It's an automatic gain control model that's modeled in the frequency domain, built upon a variable gain amplifier, so it can accurately model frequency domain characteristics and mismatch and different sneak paths through our RF front end, and then the output can be precisely controlled with this AGC model. And then we can also, we're also going to directly use it in the time domain in our data flow environment. So I'd like to show you that with a deeper dive example today. Before I do that, let me give you just a quick little overview of where we're at. The PathWave design and simulation suite of different tools, simulation tools, offers tools that can model and predict in the physics, component, and the system level. Today we're going to look at the system level, and we're going to focus primarily with our SystemVue tool. It is definitely a tool that incorporates model-based design, so you can get models from a variety of different sources. It could be a parameter-based model that's built into the tool, like an amplifier, and you provide the gain or the compression. It can be an actual circuit-based model, like it could come from our advanced design system software, circuit software. It could come from measured data from a network analyzer model, streamed measured data from a receiver. And so it can come from a lot of different sources, and we can model bits in, bits out, the RF, the channel, and the modulated transmitter, receiver, and the baseband. To kind of break it down, there's a couple different layers of how you can integrate and build a very accurate model-based system. You would start with our frequency domain circuit simulation environment called, sometimes we call it Spectrasys, or you'll see it called RF system. And that's where we can implement our RF front end. And this is where the variable gain amplifier based automatic gain control circuit is going to be implemented. And I'll show you that in the example. We can do things like even model a phased array system and project the beam into the far field. You can bring in measured data. The second level in SystemVue is data flow environment, and that's a timed domain environment as opposed to Spectrasys or the RF system as a frequency domain environment. This is a timed environment, so we can do a lot of more dynamic modeling of emission. We can inject modulated sources. We can do beam steering, a lot of different scenarios we can do, jamming scenarios, active jamming with multiple targets, those kind of scenarios. And then we can look at the output, bits in, bits out kind of output. We can look at the EVM, the quality of the signal at the receiver. We can even bring in measured data. So there's a lot you can do with SystemVue. But today we're going to focus on this AGC model that's implemented on the frequency domain and show you it in use, giving you the same quality that you would expect in the time domain model blasted with 16 QAMs of a modulated signal. So this is a list of the new features that were added as part of SystemVue 2020 Update 1. We're going to just focus on the AGC, the second bullet there of what's been added. This is the main example that we're going to use to do a deep dive into the tool is our VAR AMP AGC RF link workspace that's recently been added. And before I dive into that, let me give you a little context of maybe to appreciate kind of where you might want to, as a receiver designer, want to, you'd really need a precise, accurate automatic gain control model. So this is from our Knowledge Center application application support database. And you can basically look up this paper, and I'll have it at the end of this video. You can get the link. But basically, this was a receiver for a deceptive jamming application. And what it involved is it had an RF front end that was dual band, X band and KU band, so it went 8 to 18 gigahertz, pretty wide band. And the design incorporated like 50 channels at 200 megahertz wide each. And you had to basically condition those signals using an AGC before you went into an ADC. Otherwise, you got noise or you get saturated output and you get garbage. So AGC is critical to make sure that you condition the signal on the RF front end to go into our AGC and into our DSP to do the deceptive jamming algorithms that we needed to do. This is a more deeper look at actually how it was implemented in SystemVue. So that's just to give you a context of why an AGC is important. So let's go back to the example that's recently been introduced in SystemVue 2020 Update 1. This example has some different folders. Let's start with the RF folder. So in there is a design called RF Design. Here it is in the tree, and here it is. If I make it bigger, it shows a VGA amp, which is critical to modeling an automatic gain control circuit that's going to give you a stable output on a receiver going into like an AGC. So if I push into that model, you see that's what's been added here. It's a hierarchical model. If I push into that, you're going to see that it's built upon an amplifier in the frequency domain and attenuation control circuit that can be fed a voltage input, control input. Now, in the Spectrasys or RF frequency domain circuit environment, you can do some really interesting things, like you can have parameter-based modeling for the, like the noise figure, the gain, the compression, and you can bring in measured data or data from a data sheet showing how this behaves over these different parameters over frequency. So there's a lot of power in being able to model at that level. So let's take a look. First, we got to take this in a few stages. First, we're going to do a baseline and look at compression and noise figure. First, we're going to do a simulation of just this amplifier in the frequency domain, and then we're going to compare it against, do a compression and noise figure simulation in the data flow domain. So the difference here is we basically have the data flow design, and we're using RF link, which is basically a hierarchical subcircuit. If I push into that, it basically gets me back to the RF design. So this, if I run this data flow simulation and I compare it against the original frequency domain simulation of our VGA or automatic gain control circuit model, this is what we get. We can go to the compression curve sweep, which is in the RF folder, and you can see there is two different sets of data on here. There is this is showing the result from the purely the frequency domain simulation of desired channel power versus input power. And if I compare that against, if I go to graph 1, which that combines actually both the data flow, and which is the blue, and the red, which is the frequency domain version, you get the same results. You could turn one on or off. Like if I turned off the Spectrasys model, you can see they're very well correlated together. So at a base level, we are getting very good correlation between compression and input power between the frequency domain Spectrasys version of our VGA amp or automatic gain control amp that we're going to use it for in our receiver, and data flow. We can also compare noise figure. So there is RF sweep 1, which does a compression curve. System 1 does a compression curve. If I go over here, it's doing a compression curve to get the RF system 2. If I go there, it's doing just a normal path sweep, and that's going to give me noise and power. And from those results, I can basically plot the CNR is carrier to noise ratio, or basically signal to noise ratio, same thing. That CNR1 is at the input, CNR2 is at the output second node, and then that's the noise figure. So you get that curve from doing just this baseline VGA model in the frequency domain. If I do the same thing using the DataFlow version that uses the RF link to it, I can basically also get the data. I can get if I can go to the noise figure folder for the DataFlow, I can look at the noise sweep, and you can see it's very well, very similar results. All right, so let's move on. So we've looked at a basic level. Now we can also look at it in the third folder. We can look at it, now we can take this AGC model with confidence. We modeled it in the frequency domain. We brought it into DataFlow using the RF link component. So you see that it points to the RF design, which is the frequency domain model. And now let's basically inject it with a CW tone. And we're going to basically, it's important that we have basically put a noise density in here. So to measure the noise figure accuracy, and we also did this, by the way, on the pure RF design. We set the noise floor on the source to minus 173 .975 dBm per hertz. So that allows you to measure noise figure, the IEEE noise figure, as you would expect. And so we have a CW tone. We're going to vary the gain, and then we set a noise floor to measure the noise figure accurately. And then we have an AGC circuit that basically takes whatever the power is and then converts it to a control voltage that we can put into our variable gain amp, and we want to see if we can keep a stable output at the output of this AGC. So if we run this, it has these spectrum analyzer sinks are basically set up with continuous mode on, and so I can look at the spectrum at the input and the spectrum at the output. So let's take a look at that. Let's run this. So if we run this, we see that at the input of the AGC, we have minus 20 dBm at the peak of the marker as a signal, as a CW tone. We put a band power marker from here. Just click it down, and you can add it to any plot, like here, and you can set the tone. That's what we did here, and we compute the power on one side of the noise band, and we get like minus 117. So we can compute signal to noise from this just manually at the input of the AGC and at the output of the AGC. And one thing you'll note, this is the control voltage, right? So right now, the gain that's feeding this circuit, right, the variable gain that we have and our AGC needs to compensate for, we've set it to 0 dBm. If I increase this to like 5 dB, now let's look at the output. Now the control voltage is compensated to minus 5. So it is kind of doing as we expect. If you by the way, I forgot to mention, if you look at the notes section, there's quite a lot of good information in here on what to expect and how to exercise these different examples, and you can go through it and see what you should expect and play around and have a really good view of how to use the example. The last thing that we're going to look at is instead of a CW tone, we've kind of done a look with our AGC model on a static level. Now let's actually inject a modulated signal, a 16 clamp signal in this case, into our AGC. But now you see that we have a channel model, and we have our automatic gain control circuit here model built on a variable gain amp, but we have some different control circuitry around it. Let's look at that first. So the control, because we're injecting a 16 clamp signal, you have to basically, instead of just picking off the power and converting it to control voltage, you have to basically downsample it, get the symbols, and then do some like RMS averaging and compare it against a reference, and then you can choose what the right control voltage is in the modulated signal over what the bandwidth in this case. And so that's why we have some slightly different control circuitry there, and we can that's going to work for to set up our AGC. Now we also added a channel in there. Before we just had a CW oscillator, but now we have a 16 coamp source, and then we added a channel. So first we had some nominal loss to the channel, and that is set up by this first A3 amplifier, and it's calling something called channel loss. If I go to the equations tab, we're actually computing the channel loss as shown in line 14 of this equation. I can make this bigger, and then basically that turns into a fixed loss of like SNR of 30 dB, and so we compute the channel loss for that case, and then so we have some fixed loss in the channel, and then we're going to have some variable loss or gain or loss in the channel, and so we have a second amplifier there that right now we're just feeding with a constant gain dB that I can tune here. I'll go back to 0, and let's do this case first. So I'm going to run this simulation. By the way, the last thing I should mention is we have this digital DMOD sync that's going to actually measure the EVM, the power, the spectrum, and it also has it'll actually measure the SNR. So we're going to look at that, the input of the AGC and the output of the AGC over here. So if we run this design, now you see with 0 dB gain in that variable gain part of the channel, we're seeing 0 on the voltage. Now remember I said I set the fixed gain in that channel to be about 30 dB SNR. Now we're actually measuring about 36 SNR if you look at the error summary at the input of the AGC circuit. It says it's bouncing around a little bit, but it's about 36 dB. Why 6 dB additional loss? Well, it's because when we go through our digital DMOD sync at the input or the output of the AGC, it actually has a match filter. So it's root raised cosine filter on the transmit side that we did here, and then there's a root raised cosine on the receive side. So that's going to basically do some pulse shaping in a root raised cosine filter, and you're going to get band limit. It's going to basically throw out some of the bandwidth. And so part of that basically adds the extra 6 dB. And that's outlined a little bit more in the README file, but you can read that. But it's basically because of the filter. You know, it removes the ISI and the stuff that the root raised cosine filter does, and part of that is it removes some of the bandwidth. So that's why you get a better SNR by roughly about 6 dB. So now if I change the variable gain to like 5 again, so I do that to about 5, now you see that the control voltage has compensated, and you see that this is kind of doing what it's supposed to. Now that's all very well and good, but for our last test, let's swap out the variable gain that's kind of fixed, and let's put a sinusoid on there. You could model this in any way you want, but we want to see some variability in the gain and loss, right? So we're going to do a 5 Hertz slow varying sine wave on the gain. So if we run this, I'll set this back to 0. I guess it doesn't matter, but I'll go ahead and run this now with the slow sine wave. Now you can see that there's the control voltage is going between the extremes on the sine wave, and you see that this AGC is kind of doing what you'd expect. At the input of the AGC, you see it varying. At the output of the AGC, it's pretty fixed, and the constellation is fixed. So the AGC is doing what you'd expect, and you're going to get an accurate view of the EVM through that whole system. You know, frequency error, IQ offset, and SNR. You know, at the input and the output of the system. So the last thing that you could do, and let me do this real quick, and then we can wrap it up. But you could also just change this to a faster like 50 hertz instead of 5 hertz. Now watch what happens. What do you think is going to happen now? What's your prediction? Now it's going a lot faster, and the AGC isn't quite keeping up as fast as it should. So to fix that, you're going to have to look at, how many points that you average and capture, like the window size and the number of points that you do the control circuitry on and your filter, and then you can compensate. But it gives you a good framework and shows you, that this AGC circuit built upon the variable gain amplifier is working extremely well in SystemVue to go from frequency domain to time domain and even blasting it with modulated energy. So I hope you enjoyed that. If you have any other questions, let your local rep know or contact me, and be happy to follow up on any questions you have. Hope you enjoyed this new feature. Thanks.